Oh, I should start. I should start already. What time is it? 22. Okay, so let's not record yet. Let's just not record yet. Let's just wait another 8 minutes and. The great pleasure that I introduce Jose Alvarez, who leads perception research for the autonomous driving team at NVIDIA, where the focus is on the scalability of deep learning and its applicability to autonomous driving. Prior to NVIDIA, he was a research scientist at TRI and NICTA. Before all that, and even before the deep learning revolution, he completed his PhD in computer vision and worked on road scene understanding for autonomous driving at a time when data sets were scarce and small. Incidentally, like myself, he worked as a postdoctoral researcher at NYU under Turing Award laureate Yann LeCun, who was the very first speaker in this series 7 years ago. So this is a homecoming of sorts for him. I know we are all eager to hear his presentation, which is intriguingly titled Towards Robust and Reliable Autonomous Vehicles with Foundation Models. So without further ado, let's warmly welcome Jose Alvarez.
Thank you. Thank you, Omar. Thank you all for being here. My pleasure to be back to NYU after so many years. And today I'm going to talk about what we are doing with foundation models and autonomous driving and how we can go towards a more robust and reliable systems. The team we have at NVIDIA, this multiple research team, this one is applied research. So we sit between fundamental research and product. And the ultimate goal is to make advances in product, to make real impact, to identify things that in research can be powerful and that can contribute to advancing the product in the mid-short term, right? So what you will see today is not so fundamental, but more like on the applied side. When we talk about foundation models, I guess they are all everywhere. So this is modern AI, and these days this is happening, and you can see them everywhere, including in autonomous vehicles. And when we talk about them, we mostly talk about large and scalable architectures that can be trained with a gigantic amount of data and ideally have a general purpose that can be transferred to multiple downstream tasks, right? So in the AV field, you can see them in the architecture itself, in simulation, and in data. And today I will talk a little bit about those things. When we talk about the
हाँ अरे पर ये zip file से download किया ना
भगवान जाने वो वाला that was loud. When we talk about the architectures, one that scales very well, right, is an end-to-end system and a forerunner, and one of the main drivers of that work, PilotNet, is a small architecture that takes sensors as input and generates trajectories as output, right? The main benefit of these architectures is that can be optimized end to end. So you are actually optimizing for what really matters. And it's very data driven, right? So the more data you have, you don't need labels, or you mostly don't need labels, and you can just consume that data. And one of the main problems is that the interpretability and transparency of these models is a bit dubious, right? So you have seen probably recently that people is trying to connect some agents to these algorithms to see if we can understand what's going on. On the complete opposite side, we have these extreme modular architectures that go all the way around, right? So you have sensors, and you start doing by modules small tasks until you go to the opposite side on trajectories. The main strength of this is the explainability and the transparency of the outputs, and it's very flexible. Whenever you need to do something else, you just add one module, and probably that's going to work, right? The main problems is they are very complex, and you're usually optimizing for a suboptimal task, right? Each module you do object detection, you're going to try to be good at object detection, but that doesn't necessarily translate into being good, in this case, in trajectory prediction or planning. So one key component for autonomous driving is the planning algorithm itself, right? So for many years, and due to the lack of data, rule-based planners have been dominating all the benchmarks and the way to go, right? So a rule-based planner is basically a very structured, interpretable decision-making framework, right? So basically, humans decide what is doable and what's not, and you put a number of rules that are gonna dominate the planning algorithm. As today, they still dominate the benchmarks, especially in closed-loop metrics. And basically, the idea is you're going to simulate what the agents and the ego vehicle are going to do in the near future, and you're going to see if those simulations do adhere to certain rules or not. If they don't, that's not a valid trajectory. If they do, that's a valid trajectory. The main problem of this is the scalability. The more corner cases you find, the more rules that you may need to add, and the more chances that you don't do a good job. On the opposite side, we have this more data-driven neural planners, right? So you want to have an ML model that just consumes data, and from that is able to predict the trajectories. As end-to-end models in particular, basically are based on predicting or imitating the human driving behavior, and the only problem is that this needs a lot of data. Interestingly, these are very good in open loop benchmarks, but they are not so good in closed loop scenarios. And it's also very difficult to deal with the safety regulations for these models. So one of the questions is, can we be simple, scalable, data-driven, and at the same time safety compliant? On the opposite side, so that's on the model side. On the other side, we have the data. We need a lot of data, right? And all these foundation models are trained with a gigantic amount of data. If you think about the exponential growth in the data is impressive, right? So there's a trend to try to minimize or try to contain the cost. And usually when we think about cost, we think about labeling, but you also need to think about the storage and training cost, right? And on top of that, creating the data sets for training those algorithms is tricky, right? So if you don't pay attention to what data you select, what is going to happen is that you have a very skewed data set that is not going to do what you really want to do. So what needs to be done on the data side is first, assuming you have a large pool of data, can we select what data really matters for our problem? And then if we don't have data, can we go out there and increase more data? To give you a reference point, right? So to train a foundation model, a video foundation model or a clip model, we may need to we may need to select 1/10 of the data set by reducing the redundancy on the data set. We start with maybe 10 billion data points, and from that, we try to go to 700 million, or something like that, which will be the final training set. How it's done usually is, for instance, we have some data and we run some visual embedding, a clip model, and we're going to try to compute some distance to remove redundancy, right? So points that are very close in the space, they will be reduced. Like we only select one, and if they are far away, well, we can assume that they are diverse. The idea behind is that this has some implicit semantics, and one of the problems is that they are implicit, so we don't really know what is happening, and the clip is a fixed embedding. So whatever you do, the embedding is going to be the same. What we see here is an example of three images of three similar streets, right? And with these embeddings, what we find is that the distance between the three images is very similar. However, if we look closely, the two top images do have pedestrians and the bottom one does not. So ideally, we may be interested in separating these two. And with these clips, with these visual embeddings, we cannot really do that. So what I'm going to talk about today is first, can we generate better architectures that are more simple and more scalable, that sit between this end-to-end monolithic architecture and these super complex modular-based approaches that can integrate both data-driven and rule-based methods to just be scalable and safety compliant. And on the other side, I'm going to try to talk about how can we use foundation models on the data side to try to create the better data sets, the best data sets that we can, and try to convince you that at the end of the day, if we do a good selection, we will be able to outperform like random increase of data, and the better and the less data, but more diverse data that we have, the better performance we're going to get. And obviously, less data is going to translate into less training cost and less compute and less storage, right? So I will quickly talk about three things that we have. One is this Hydra model, this end-to-end driving architecture. Then how we can use a foundation model to add some interaction with the system, and a data engine that we have to create better data sets. And after that, I will talk about some challenges that we are currently working on and that sit on top of these three existing approaches. Let me start with this end-to-end driving with expert-guided Hydra distillation. The idea is very simple, right? So instead of having a monolithic architecture, can we actually have a non-monolithic two modular blocks? One is perception and the other is the trajectory prediction. And the idea is that with the perception module, we're going to be able to explicitly understand what is going on in the network. And we're going to be able to have multiple levels of supervision. On the one hand, we can supervise with perception. And on the other hand, we can supervise with the ultimate goal, which is the trajectories or the path planning, right? In this particular case, Hydra explicitly models safety. And we're going to do that by integrating, as I said before, rule-based teachers and the imitation learning as end-to-end classical systems. With this, what we did is participate in one of the challenges, and we actually got very good results in June at CEPR. So let me tell you a little bit more about this. One of the key components is this idea of, instead of predicting a single trajectory, can we predict a distribution of trajectories, and each of them, how likely is to be compliant with some rules, right? On the one hand, one trajectory will be the most similar to the imitation learning, to the human trajectory that we should be taking. And on the other hand, we're going to see how compliant that is with rule-based teachers, right? In no particular case for the challenge, what we did is follow exactly what is closed loop evaluation, right? So are we going to create a collision? Are we within the drivable area? Is a comfortable trajectory? And those are going to be, we're going to have teachers that are going to select what trajectories are more likely to be compliant with these metrics. And at the same time, we're going to have the pure imitation learning trajectory. So if we combine these things, we will finally select the one that is more likely to be useful. What we found out is that actually we can scale this. We don't have to only limit ourselves to these basic rules. We can expand that. For instance, we can have a traffic light compliance metric. Basically says if this trajectory is going to run a traffic light, well, don't choose it. Choose something else. Or can we see how much are we deviating from, let's say, the center of the lane? Or are we within the driving area? Are we keeping the distance with the car ahead of us? So what we found is that if we do this and we put everything together, at least on public evaluations, for the first time, we can actually beat rule-based teachers when it's in terms of closed loop evaluation. What is more relevant is that this approach also scales with the size of the backbone, right? So in the bottom two rows, what you see here is that the larger the backbone, especially if it's pre-trained with depth, what we can get is much better accuracy compared to other methods. So here we have a couple of examples. One is a right turn, not very critical. And the other is how we can do a left turn and how we can actually manage to understand there's a space there and we can go ahead and make this unprotected left turn only with vision, which is pretty impressive. So now we have this model that is trained end-to-end and can consume a lot of data. So one other thing that we can do is, can we actually add an LLM agent that allows us to first interpret what the system is doing and also ask questions, right? So can we actually reason and plan and do user interaction with the system? So what we did in this case is, well, we get a very strong multimodal LLM, and we're gonna add that into a 3D reasoning, which is what we need for actual planning in driving, right? So instead of using a 2D image, what we're gonna do is project the features from the 2D images to the 3D world and use them with the multimodal LLM. If we do this, what we get is pretty nice results. In our case, we also trained this model with counterfactual reasoning, which added some robustness to the system. And what we can see here is an example where the model is telling us what is the rationale behind of what is going on. The other thing that we can do is interact with the model, right? So instead of the model tell us what is going on, we can ask questions and the model is going to answer the best they can. So this is pretty interesting. And we added one more thing, which is this counterfactual reasoning, which is try to understand, okay, if I'm going to do this, what are the consequences? Should I do this or not? And the model, as you can see here, is saying, well, if you follow this trajectory, probably is not the best you could do. It's not a safe trajectory. This is very impressive. And we thought, okay, does the system really reason and help us planning? And as you can see here, well, this is an example of system-initiated lane change, right? So we have an image and we ask, what should I do? And the system say, well, you should stay on the right lane, or you should move to the left lane because there's a line that the lane is closing. So it's very impressive. However, if you look in detail, you can choose some other examples that are not so impressive. And what happens is that every now and then the model is going to create things that actually are not grounded to the visual contents of the image. In this particular case, we asked the model, can you explain what's going on and what rules should we follow? And in red, we see here that, well, it's talking about some pedestrians that actually are not in the image, right? I remember when we got these results, people was very excited, and I was asking, are there really pedestrians in the sequence? Is the model that smart that is remembering that there were pedestrians, so they may appear? No, actually, there are no pedestrians. So for me, that questions the reliability as today of these models. And I will talk a little bit later within the challenges. So with that, let's move to the data side, right? So, and in particular, we have been working on this holistic data engine. And how can we use foundation models on the data side to create better models? Again, if we recall what the ultimate goal is, instead of having big data, our desire would be to have smart big data. We have a pile of data, gigantic amount of data, and we need to be able to select what is really relevant for my task. And then if I don't have the data, or if I need to access new data, what exact data should I access or should I create, or to expand my data set to continuously improve my model? So instead of using visual embeddings, what we thought is, well, we can use foundation models and language encoders to create a holistic description. Instead of having this fixed representation, now we can use one of these models to create a detailed representation in natural language that has explicit semantics of the contents, right? So if you can see here, is a detail with the representation with language of what's going on. In particular, we not only use the visual data, but we can also use anything that is available, metadata that is available in the car, such as the ego vehicle or the predictions that the car has done. If we input this into the foundation model, we're going to have a much richer description. In this particular case, depending how we do the prompt, we're going to get different answers. So that means that we will be able to adapt the embedding to whatever final task we are looking for. If we do clustering of the embeddings, different from before, now we will have a clear description of each embedding. And that's going to be very useful, as we will see later, to either reduce the amount of data or to go out there and collect more data. Let's see an example here. As before, we have the same three images and we can see the comparison between the holistic distance and the visual distance. As you can see, if we use the holistic distance, there's a difference between the first top two and the third one, right? So there's the algorithm is able to capture the details in terms of the pedestrians that they are in the image. What we found out is that if we use this at the scale, we can actually reduce 30% the amount of data and still get very good results. And more interestingly, what we found out is that with this method, we can get a very diverse, and it's better to have a very diverse set of data, even if it's fewer examples than larger amount of data that is redundant. What we see here is that with one of the underrepresented classes, we don't need more data. We actually need diverse and valuable data to get good results. So the second thing that we wanted to do is, now that we have a compact data set, can we go out there and expand our data set? Now we have a natural language description of what data do we have. So if we need something else, can we try to find that data in a data lake or existing unlabeled pool of data? So if we do that, what we found out is that we can actually use these foundation models to query actions and try to understand what actions we need to retrieve. In this example, for instance, we want to find cut-ins, right? So we want to find cars that are cutting into us and interrupting or driving. In this second example, we want to find a slowdown because there's a vehicle in front of us. So as we can see here, if we use these foundation models, we're going to get very good results. Of course, what matters now is how do we include this into the training set, right? So if we expand our training set, what we obtain is much better results than if we were using random selection, and we're gonna get with the same training cost and the same storage cost. And again, what we observe is that for underrepresented classes, we can get much better results even with fewer examples. So if we move from in the car to the data lake and the data engine, what we can do is leverage existing off-the-shelf foundation models. We don't need to train anything. We can use just them. And there, we don't need to worry about the reliability. This is not safety critical. So an error in the selecting data is not going to be translated into those accidents or any relevant problem, right? However, first, we can see that it's sensitive to prompt variations. How we ask the system to generate embedding is going to have different embeddings. And it's particularly difficult to deploy these models efficiently, right? So we have a huge amount of data and we want to save money and storage and training and whatnot, but we are using these massive models to characterize the data. That's a little bit contradictory. So we need to find ways to deploy this on the edge. So this is what is going on. And there's a number of challenges that we found along the way that we keep working on them, right? First is, well, how do we do with corner cases? So, and especially these days of Gen AI, right? So do we collect data or do we generate data? So before in the data engine, we were talking about, well, we're going to go to the data lake and we're going to find data. What happens if we don't find the data? In our case, we have a natural language description of what we are looking for. So one option would be to go and to tell data ops, this is exactly what we want. So these cars are going to go out there and collect new data. Another option is, well, what if we don't have that data? Can we create image data that represents what we're looking for? So we were exploring novel view synthesis for that. And please recall that at the end of the day, what we want is generate that data to be included in the training set such that the modeling increases the performance, right? So this is very important. One of that involves two things. First, it needs to be efficient and scalable. And second, we need to understand how much data do we need to generate. If we have 700 million points, now how much data do we need to generate from a corner case to make a difference when we train the model? So what we see here is two examples. One is MRNerve, and the other is using a wall sheet. One moves the point of view and the other changes the sensor. And we were considering this to create models that are robust to sensor placement or sensor variations, right? So if we collect data with one sensor, can we transfer this to a different sensor? Interestingly, what we found out is that if we generate this data, definitely there are many artifacts. And the question is, are our networks robust to these artifacts? Keep in mind, first, this is going to happen or is happening with diffusion models, with these novel view synthesis systems. Anything is, as today, is generating artifacts. And we want this data to cover those where we don't have data. We actually, those corner cases, probably critical situations. So are all networks ready to deal with these artifacts? That's one of the challenges. So instead of going in that direction, we thought, what if, let's say, we are looking for collisions? Instead of generating visual data, can we generate geometric data? So we can, again, use natural language descriptions to generate the scenarios, in this case, collisions, that are going to resemble critical situations. With this, we can actually inject this data into the planner of our Hydra model and find out that if we force the system to not imitate these collision situations, we will be able to reduce the collision rate. So we are creating a safer model, in this case, without the need to go all the way to visual input. Here we have one example. Keep in mind that this is non-reactive, right? So if you look at the ego vehicle in red, what you see on the right is that the ego vehicle stops because the car in front is slowing down. So it's doing a pretty good job. The second challenge, and is a very big challenge, is these hallucinations, right? So we were talking before this case of pedestrians next to a bus. And here is another example where we ask the model, describe this, and all of a sudden, well, it talks about a table. I don't see a table. It talks about two people. There's no two people, right? So what's going on? And how can we work with this? I mean, if we are thinking of using this in safety critical applications, definitely we need to mitigate this. So in that end, one of the first problems or the challenges that we have is how do we benchmark hallucinations, right? So at the moment, most of the metrics, most of the methods to benchmark this are based on image level compositions, but they do not take into account the object interactions, how an object is interacting with other objects or with their attributes or whatnot. And also, existing benchmarks do not capture the consistency. So they usually use one positive question: is there a bat in the image, or is the shirt blue? And one negative question, but not many. So there's no consistency in the evaluation. Instead, what we want to be really reliable is, can we understand the composition at object level? Can we understand the attributes of an object? Can we understand how those attributes relate to the object and how two objects are placed in the image together? And can we also evaluate if the model is consistent, is giving consistent answer or not? And we can achieve that by asking multiple negative questions, right? So if we focus on one of these, for instance, in the image is blue, in the image is pink, in the image is green. So there are three negative questions. So the model should be consistent to truly give us the idea that they are doing a good job, right? And not just one. So once we have a benchmark, the next thing would be, can we mitigate this problem? So how can we know how to evaluate? Can we mitigate this? Most of the algorithms out there are based on retraining these foundation models. But as you can imagine, that is very, very costly, right? So is there any way to do this with an off-the-shelf model without the need to retrain it? So the first thing what we have been doing is, can we understand how hallucination and biases are related? And we found out that actually there are three types of biases that produces these hallucinations. One is text to visual, that basically means the text is overweighting the visual information. And this may happen because usually these models are pre-trained, heavily pre-trained on text, on language, text-based pre-training, right? So that means that the text is going to dominate the visual information. The other bias is the co-occurrence. So in the case of the bus, usually there's a pedestrian next to the bus. So the model is just using the statistics from the training set to output things that they think they should be together, right? In this case, in the image, what we see is that it's creating a knife because there's food. So probably that usually is together, goes together. The last type of bias, we found out that the longer the description is, the more chances that the model hallucinates and create fake descriptions. So we might need to find a way to reduce that. So what we have been working is, can we actually, instead of retraining the model, can we understand the influence of each token into the hallucination? And if we can do that, we can probably shift the influence of each of these tokens and mitigate the bias. And if we do that, we're going to, at the same time, mitigate the hallucination, right? So here we have an example where by just changing the influence of each token, what we're going to change is the answer of the model. And as you see here in the example, we're going to reduce the 3 types of bias. So we were talking also about reasoning, right? So we said, well, it's pretty impressive that the model understands that there's 2 lane closures that they need to move. On the right here, there's a hard case in the image. There's a corner case, and we ask the model what's going on, and the model can say something that is meaningful and seems that the model is reasoning. At the same time, however, we can ask for, give us pedestrians in front of the vehicle, or can you find a narrow street with pedestrians? And as you can see here, there's no pedestrians. However, in the 3 cases, there's a pedestrian sign. So the model is good at reasoning to some extent, but it's still confusing these basic things of a sign versus a real pedestrian. So for us, this is one more challenge that we need to deal with. Last but not least, right? So how do we deal with the robustness to auto distribution? So by robustness in this case, we don't refer to completely shifting the distribution, but there's nuances in the image data that may cause our problems at inference, right? Generically, this will be noise, just some sort of noise that we haven't seen during training. That's why we call it zero-shot robustness. And this is affecting mostly perception models, in particular in 3D models, right? So one thing that we found out is that the larger the model, the more robust is to these variations. But still, if you check the retention ratio, like the ratio between the accuracy of the model with clean data, exact data as was used for training, and data that has been perturbated slightly, what we found is that there's a drop in accuracy. What is interesting is that the more compact the model, the larger the drop in the accuracy. And that's very undesirable, especially if we want to deploy our models in the cloud or efficiently, in the car or efficiently in the cloud. What we would like is at least to be able to maintain this retention ratio to make sure that the model is able to perform no matter what the noise in the image is. So one way to reduce the size of the model is through neural network compression. And what is interesting is that these 2 things seem to be orthogonal, right? On the one hand, if we want to be robust, probably we need to be redundant. And on the other hand, if we want to be compact, what we want is to reduce redundancy. And that means that we are somehow going to overfit to the data set that we have. So what we found is that one way to move forward is maybe we can do a joint optimization between compression and robustness. And if we do that, especially taking into account the shape of the landscape, what we can find is models that are much more robust, even they are compact. Now, the question is, does this also happen with these foundation models? Does this also happen when instead of doing perception, we are working directly on the end goal, which is the planning or the trajectory prediction? Are we able to make these models compact and still maintain the auto-distribution characteristics that they do have? Are we going to be able to characterize data even we have changed the size of the model? So this is for us something that will be interesting to understand if we can maintain this. So in summary, first, we talk about a simple but scalable non-monolithic architecture that is able to leverage rule-based and data-driven approaches. We describe how foundation models, as they are today, are very useful to select and curate rich and diverse data. And if we do so, we're going to find an optimal data set that is that has fewer examples, but they are more diverse and richer, so they're going to produce much better results. And among the challenges ahead, the first one is, if we're going to use data generation, can we deal with the artifacts that these generative models are causing? And how much data do we need? And how are we going to distribute that data to make it efficient for our model at the end? How do we deal with the hallucination such that we can create safer models on the edge, especially without retraining? And can we not only focus on the performance of the models, but also on the robustness and how the robustness characteristics of the models do transfer when we transfer these foundation models to downstream tasks? And of course, this was not only my work. There was a lot of people involved. So thank you all for that.
Time for a couple of questions.
Hi. Actually, I have a question about the holistic instance. You use holistic instance to select data. So basically, you use LLM and give language descriptions of the text. So, but their tests, how do you convert it to scalar?
So you have the language encoder, right? So with the foundation model, you generate the text description, and you go from text to an embedding. And that's where you compute the distance, the actual distance.
Hi, Dr. Alvarez. I'm very curious about what kind of data these foundation models are trained on. For example, there's something called LiDAR. So, but Tesla, very famously under the leadership of Hydra-MDP, moved away from LiDAR. Now they rely only on a vision system. So what do you see as the future of these autonomous? I mean, should we be relying more on LiDAR, or do you think there's going to be a combination of LiDAR and vision systems as well?
So yeah, it's a good question. For 3D reasoning, you need depth, right? So somehow it would be good to have LiDAR. At the scale, probably there's going to be more visual information than LiDAR. So it would be good to use visual information and move away from LiDAR if possible. But the depth is still a challenge, right? So if you want to really reason at a distance, that's going to be a problem. Please.
I wanted to ask how the agent is reacting to real-time data when it has decided a set of instructions from beforehand. Is it not reacting?
Say again, sorry.
Is the agent reactive that is coming up with the instruction to drive to any place in this case?
So at least so you're asking, is the system reacting, the agent?
Is it reactive, or is it coming up with decisions on its own before things are happening?
So the one we have is non-reactive, right? So at the moment, it's non-reactive. So it just understands and tries to explain what's going on in front of that. That's the one we have at the moment.
I do have a question about the, you mentioned in the beginning this rule-based kind of, distillation before the prediction model, right?
Yeah.
So why don't just do as to add? I guess my question is because in my mind, the whole point of end-to-end is to eliminate the need to have rule-based description of the word, right?
Yeah.
So for example, you're talking about the lights. You're saying that, there's a rule that if you have a red light, but it's not all through. But I could imagine a situation with human drivers where all the lights are red because, for example, there is some problem with the traffic lights, and then usually what the human driver would do is would just try to, slowly go through the crossing, being mindful of that other thing also to go. Whereas I would see that the autonomous driving system would just have a hard-coded rule that, okay, there's a red light, so we can't go, which all it would do is just jump in traffic, right? So why do we need this rule-based, right, how do you even generate those? Because this is, it's like you're trying to generate the description of the word.
So might be
Synthesize the description of the word.
might be a problem of the amount of data. So I guess your assumption is that we have enough data that can describe all possible situations. And we can learn from that.
From this table, so how your rule-based, the system that incorporates the rule-based, how does it compare with just a pure pilot app?
It does. I mean, the numbers does better, especially in closed loop, does much better. So at the moment, imitation learning in closed loop, they are not very good. Rule-based is systematically doing better. That can be a lack of data, right? So it's not that
Right.
anything else than that, right? So the rule-based is just helping to have more signals to what not to do. Because imitation learning systematically is saying what you should do. And the rule-based may be saying this, you should not do this. So that's a little bit complementary in that space. If you have enough data, it could be possible that you have bad behaviors as well that you could integrate there and not imitate.
So you're saying that the systems that incorporate to some extent the rule base, they are less data potentially likely.
At the moment, yes. Benchmarks are limited at the moment, right?
And then the other question I have is regarding when you talk about the sampling and the vision, right, the holistic, I guess. So you're saying you're showing this picture where basically the indicator of the difference was the presence of the pedestrians, right?
Yeah.
So just to clarify, so how does the system know that the pedestrian factor basically is it automatically learned?
So in the description, the way we prompt, we are going to ask specifically what a number of things that are going to describe holistically the image, but then detail are there pedestrians or not, or is traffic?
So you kind of, okay, so
There's a lot of prompt engineering there that is going to.
so it's not scaling right now that much, or is it?
That part,
Because because I would imagine that then, so since you use it for something, you need to define the concepts that the system needs to pay attention to in order to be able to.
the way we have done that is generic enough. But yes, I mean, intuitively, you could always add one more description, right? So you can just expand your embedding, but it will not be the most scalable at the moment.
But I guess in this example, the reason you pay attention to pedestrian because obviously you don't want to go through it.
Yeah. So in the prompt, there was pedestrians. So it's saying, are there pedestrians or not?
I guess I just don't see how it's scalable then, but you're saying. Okay. It's in the paper.
It is, yeah. It's that's now in archive, right? So those details are there.
Okay. I will let somebody.
Yes.
So it's very well hallucination.
Yeah.
It's not beneficial to have a selective filter on the dependent to filter the visual stimuli like how humans have selective attention.
Say again.
Like how humans have selective attention.
Yeah.
It is not beneficial to have a selective filters on the different embeddings and the that particular filters image can be queried to the LLM so that will reduce.
How would you?
So we can jointly train the filter with the process.
I guess. But then you need to jointly train. Yeah.
That we have a selective part of the image which we really want to see. That's how humans focus on specifically.
Yeah, but I guess
can be used
it could.
Yeah.
In no particular case, we were trying to be as generic as possible, right? So without training, these large models, these foundation models are very good at corner cases, are understanding things that you have never seen, right? So without training, can we do that?
Now we are not training the LLM evaluation. giving additional context on in form of an image or the network is actually seeing.
But if you use clip is only visual, right? So how are you gonna do that?
Okay, after the clip embedding, we have a filter.
Yeah.
And the output of the filter we give it to the function.
Yeah.
So that we can jointly train the clip, jointly train the entire network, and get the output. Now we have the ground truth image along with the filtered image, and query the LLM. Okay, this is my point of interest right now, and what is the can you describe based on these important things? So that would reduce the hallucinations of the.
So I guess that's okay. I guess that will be similar. So with the metadata, we are doing something similar. So we are focusing the attention, or we are changing the prompting based on some metadata that is reducing hallucinations. So yeah, it should be similar. Yes, that's all.
Okay, let's have the last question and then
Sure.
last question.
So I guess I missed this important point. Are you reintroducing the LLM embeddings into the model, or are you just using it for describing the image embeddings?
You mean for the data engine?
Yeah, I mean for the policy model.
Mhm.
Using the direct trajectory.
Yeah.
Are you using the LLM embeddings to choose the directory?
Yeah.
Or it just okay, you are using it.
Yeah.
Okay, so it's kind of like a contextual kind of selection, right?
Yes.
So a general criticism is that it can just lead you into believing that it's thinking in one way by actually using some different like reasoning to actually use the trajectories. Because you're using a decoder to actually understand the text embeddings, right? And that can add a lot of bias in itself.
Yeah.
How can we?
So I will not trust it. Yeah. Yeah. As today, I will not trust it yet.
Okay, let's thank the speaker again. For you, so let me know. Remember else, and maybe let's just step with the photos.
Sure. Also nice.
Course.
Sorry. Okay.
You may want it in front of the chair, right? It's in front of the media.